Professor Sugisaki, shall I begin?
Yes.
Okay, thank you. So hello everyone. We welcome you to the 8th and final lecture on the lecture series Quantum Chemistry on Quantum Computers by Professor Sugisaki. Today's topic would be techniques for resource and error reductions. And they include topics such as symmetry adaptations, quantum circuit optimizations, Trotter decomposition error reductions, etc. Professor Sugisaki.
Thank you very much, and welcome to the final lecture of the lecture series on the quantum chemistry on quantum computers. The title of today's talk is Technique for the Resource and Error Reductions. And today I'm going to talk about mainly 3 topics. First, I would like to discuss how to reduce the number of qubits for wave function storage. Next, I want to discuss about the quantum circuit, the quantum gate reduction, or to make the quantum circuit shallower. And another topic is the total error reduction. And these techniques are very important, especially in the nuclear era, because the quantum computer currently available is very noisy, and the number of qubits is very limited. Only small number of qubits can be accessible. So it is very important to reduce the computational cost to obtain reliable results or meaningful results from the quantum computers. So let's start by thinking here a example. First, he thinks to execute 6 qubit VQA on real quantum devices, but he can access only 5 qubit systems. So he wants to reduce the number of qubits for the function mapping. Another situation is something like this. She wants to carry out the quantum simulation of the time evolution, but the quantum circuit is too deep to execute. So she wants to make the quantum circuit shallower. So how to do such thing? Another situation is something like this. In this case, he performed the quantum phase estimation based for I, but the obtained energy is somewhat different from the computer by using traditional quantum chemical calculations, like Gaussian or games or something. And he suspects the total decomposition is the error result, main error result. So how can he make the total decomposition error small? So today I'm going to talk about these 3 topics. And first, I would like to discuss the qubit reduction. Actually, I already introduced some qubit reduction technique. So here, you can find the similar slide in the 4th lecture. My slide of the 4th lecture on the wave function mapping. In this case, we consider the Hamiltonian of the hydrogen molecule with the SO3G basis. So the system consists of the 4 spin orbitals. And the Hamiltonian can be written as shown here. This is a qubit Hamiltonian. And F1, F2, and so on question of the corresponding power operators. So in this case, but if we perform the Bragg-Kitaev transformation, this is a qubit Hamiltonian obtained from the Bragg-Kitaev transformation. But in the Bragg-Kitaev transformation, the allowed configuration for hydrogen molecules for spin singlet states are 1000 and 0010. So it means the second and fourth qubits are always 0. So we can exclude the second and fourth qubit from the computation because the quantum state doesn't change from the source state. So in that case, we can map this original 4-qubit Hamiltonian into 2-qubit Hamiltonian. So here I would like to generalize this kind of approach for this is just a particular system case of the hydrogen molecule with SO3G bases. So I would like to generalize this approach for to make applicable for any molecular system. So first, basically, John Wegener or Bright-type particle basis requires the N-orb of qubit, where N-orb is the number of spins. So because these approaches are fundamentally based on the occupation number basis and transform the occupation number basis to some different basis. So generally, we need N-orb of qubit. And let us think about the Hooke calculation of the spin singlet state of hydrocation molecule. So in this case, the system has 2 electrons, and one is spin up and one is spin down. And the allowed configuration are written here. The wave function can be represented by a linear combination of 1-1-0-0 state. This corresponds to the Hardy-Fox determinant, and 0-0-1-1 configuration. This corresponds to 2 electron excited configuration from the Hardy-Fox wave function, and also 0-1-1-0 state and 1-0-0-1 state in Jordan-Wegener cases. As I said before, this molecule has 2 electrons, and one is spin up and another is spin down for spin singlet state. So it means the number of qubits in the one state of Q1 and Q3, which tracks the occupation number of spin alpha electrons, is always 1. And usually the number of qubits in the one state is also called as a Hamming wave. And also the Hamming wave of the Q2 and Q4, those qubits tracks the occupation number of spin beta electrons. It's always 1. Okay? So it means that if the Q1 is in the 1 state, we can say that Q3 is 0 state. And if the Q1 is the 0 state, then we can safely say that Q3 is the one in the 1 state. So in this case, the Q3, quantum state of Q3 can be represented by using the quantum state of Q1 as shown here. So by applying this approach, we can reduce 1 qubit, in this case Q3, because the quantum state of Q3 is dependent on the quantum state of Q1. Again, for spin beta orbitals, if the Q2 quantum state of Q2 equals 1 state, we can safely say that Q4 is in the 0 state, and vice versa. So by applying this symmetry, we can reduce another 1 qubit, in this case Q4, because the quantum state of Q4 can be written as 1 minus Q2. But unfortunately, this two-qubit reduction scheme is possible in Jordan-Wegener cases, but it's not so efficient. I will explain in this slide. Let us think about the water molecule with SO3G base. In this case, we have 7 molecular orbitals, and we need 14 qubits. But we can reduce 2 qubits, so we can map the function of this system by using 12 qubits. But in this case, we can deduce the Q13 because the quantum state of Q13 depends on Q1 and Q3 and Q5 and Q7 and Q9 and Q11. And in this case, if we think about the spin singlet state, the number of spin up electrons are 5. So the quantum state of Q13 can be written as shown here. Again, the quantum state of Q14 is also written as shown here. But as you can realize, if you understand, realize the quantum state of the 13 qubit depends on the quantum state of 6 qubits. In this case, Q1, Q3, and Q5, Q7, and Q9, and Q11. So basically, we can reduce Q qubits by using this approach, but in this case, the Hamiltonian transform Hamiltonian becomes more terms because let's think about the calculation expression value of the Q13. Let's think about the number operators of. In this case, the number operator acting on Q13 can be rewritten by using the number operators of Q1, Q3, and Q5, Q7, Q9, and Q11. So in this case, we can reduce the qubit, but the Hamiltonian becomes somewhat complicated. And I can say that the qubit reduction is more easily efficient for both type and particle basis. And some general introduction of the qubit reduction scheme were introduced in this paper. And let us think about the Bragg-type transformation cases. And the Bragg-type transformation matrix for 8 qubit system written as shown here. And let us think about the spin orbital system with n alpha and n beta for spin up and spin down. N alpha and n beta represent the number of spin up and spin down electrons. And usually we use the alpha beta form for the wave function mapping. So it means that we have 4 molecular orbitals and must this n, small n, corresponds to the occupation number of the spin orbital. In this case, 1 alpha and 1 beta and so on. So we usually use this kind of wave function mapping. But in order to utilize the qubit reduction scheme, first we rewrite the quantum state transform the quantum state from alpha beta format to alpha beta format, as shown here. In this case, first we write all the quantum state corresponding the spin alpha electrons, and then we write the quantum qubit trying spin beta electrons. And this is just an occupation number base. And then perform the Bragg-type transformation. By applying Bragg-type transformation, we can obtain this kind of quantum state where Q1, Q2, Q3, Q4, and so on depends on the occupation number of this wave function. Importantly, first, you can see that this Q4, so the quantum state of Q4 shows the sum of the occupation numbers of spin alpha electrons. In this case, N1 alpha plus N2 alpha plus N3 alpha plus N4 alpha. So it means that N4 equal N alpha modulo 2. And also the Q8, this qubit, stores the number of all electrons, I mean the n alpha plus n beta modulo 2. So in this case, if we specify the system, we can think about the X-spin orbital systems with 2 spin up and 2 spin down system electrons. In this case, Q4 is 2 modulo 2 equals 0, always 0. And Q8 is also always 0 state, because in this case, the n alpha equals 2 and n beta equals 2. So the Q8 equals 4 modulo 2. So Q8 is always 0 state. So in this case, because the Q4 and the state of Q4 and Q8 don't change during the computation, as long as the ionization operator is applied. So we can exclude this qubit from the computation. So in order to reduce the qubit, so we have to rewrite the Hamiltonian also. So we think about this HTGT corresponds to the target Hamiltonian of the target state. And if we can apply a unit operator to generate the H scheme, where H scheme in H scheme, the H scheme is represented by a linear combination of power operators. In the H scheme, the fourth and eighth operator is always sigma k. So basically, this kind of transformation is always applicable. And also, this approach can, in this case, we apply this approach to the number of electron conservation rule. But we can extend this approach to point group symmetry. But anyway, let's think about the parity basis. And again, we can first we rewrite the quantum state from by using alpha beta formal action here, and then perform the step for parity basis. We can obtain this kind of quantum state. Again, in the parity basis, the qubit stores all the occupation number before the, in this case, for the fourth qubit, stores the sum of all the occupation number between Q1 to Q4. So Q4 is always n alpha modulo 2, and Q8 is always n alpha plus n beta modulo 2. So we can reduce 2 qubits by using efficiently reduce 2 qubits by using step and parity basis. And this approach, and also I would like to say that this kind of 2 qubit reduction scheme is applicable only for the non-relativistic calculation, because in the relativistic quantum chemistry, the spin quantum number x is no longer a good quantum number. And instead, we have to think about the total angular momentum quantum number j equals a plus s. So in non-relativistic cases, the j becomes a good quantum number. So, and j can be, but s spin quantum number for electron is either 1/2 or -1/2. But j can be, let's say, 3/2 or 5/2 or something. So in this case, if the j becomes a good quantum number, this 2 qubit reduction scheme cannot be accessible, because we can say that the spin alpha and spin beta is not a good basis. But in this case, even in this case, we can say that we can reduce one qubit because the number of total electrons is already conserved in the computation. So in this case, we can apply in the relativistic case, even in the relativistic case, we can reduce Q8 because the Q8 plus the occupation number. I mean the number of electron module 2. So this is already constant for quantum chemistry problem. And this qubit reduction scheme is first applied for the electron conservation. But this kind of approach can also be applied to the point group symmetry to reduce the qubit. So I can say that using the conservation rule of the spin alpha and spin beta electrons, we can reduce two qubits. But if the molecule have some point group symmetry, in this case, we can reduce more qubits. And when I think about the molecule in CQV point group, such as water molecule, therefore, irreducible representations. And these four irreducible representations can be discriminated. For example, by using C2, this corresponds to 2-fold rotation along the z-axis, and sigma v is C. It corresponds to mirror image on the xc plane. So in this case, the Hamiltonian is block diagonalized, of course, and to make each block diagonal space contain only the A1 or A2 or B1 or B2 operators. And this operation can be discriminated by using C2 and sigma v operation. So in this case, we can reduce two qubits in order to stress the one qubit stress the symmetry of the C2. And another qubit stress the symmetry of sigma v is C. This qubit can be reduced from the computation. So basically, this approach corresponds to the block diagonalization of the original Hamiltonian to the reduced representations. Maybe some of you may wonder how to define this kind of unit operators. But this kind of unit operators, in order to derive this kind of unit operator, you need some knowledge of the Clifford group transformation and stabilizer code. This approach is somewhat complicated. So if you are interested in, please refer this paper for details. And next, I would like to discuss quantum gate reduction. In the quantum circuit construction, I introduced that these quantum circuits, basically A and B, are equivalent. And in the quantum chemical cases, we usually use the quantum circuits of this type A, because type B quantum circuit includes some non-nearest neighbor single gate. But this kind of transformation can be used to reduce the number of single gate in the time evolution of quantum circuit corresponding to time evolution operators or electron excitation operators in unit coupled answers. So also, I can say that by using this kind of equivalence, we can say that this function circuit C is also equivalent to the function circuit depicted A. Okay, so we can use this kind of operator equivalence to reduce function G. So let us think about the time evolution operators using of this kind of two electron operators. The quantum circuit for corresponding to this kind of operate this kind of time evolution operator can be written as shown here. Here, M1, M2, M3, M4 should be H, Y, 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 and H, Y, H, Y, and Y, H, Y, H, Y, Y, H, H, and H, H, Y, Y, and Y, H, H, Y, and H, Y, Y, H. And here, H corresponds, means agamma gauge, and Y corresponds to the quantum gauge that interchange from the Y basis to Z basis. And quantum circuit corresponding to this operator is generated by using this kind of quantum circuit as a one set. First, we apply this kind of quantum circuit using agamma operators for M1, M2, M3, M4. And then after we perform this same structure of quantum circuit with Y base, and then perform another same kind structure of quantum circuit with HY, and YH, and so on. Importantly, the qubit, two qubits between P and Q, this qubit, and qubit between one qubit between R and S, this one. These three qubits affect only the parity. I mean the qubits corresponding P, Q, and R and S. The quantum state can be changed by the time evolution operator. So basically, this operator corresponds to two electron excitation. So applying this kind of operator to, for example, 0, 0, 1, 1, we can obtain some linear combination of 0, 0, 1, 1, and 1, 1, 0, 0. So the occupation can be changed. But these three qubits affect only the phase. I mean the parity. So by using the this kind of quantum gate regression scheme, we can rewrite this quantum circuit as shown here. So in this case, we can this string of Lager is decomposed to two types of string of Lager, and one is inside of the M operators, and another one is outside of this of the M operators, and the string of Lager inside of the M operators affect only P qubit P, Q, R, and S. And the string of gauge acting on the qubit between P and Q, two qubits between P and Q, and one qubit between R and S are located outside of the M operators. And also, we have to use the control power Z operator instead of the single operator in this case. But anyway, these quantum circuits are equivalent Okay, so by using this kind of transformations, the quantum gate in blues are cancelled out when subsequent applying the circuit with above this 8 set of M operators. So let me illustrate using this slide. As I said, that the quantum circuit divided in left and right are equivalent. Because writing this kind of quantum circuit is some time consuming, so I would like to use this kind of cartoon to represent the quantum circuit. So the time evolution operator using the original quantum circuit can be constructed as shown here. And actually, for 2 electron excitation operators, we have 8 sets of this kind of operator, gauge quantum circuit. So we need MAV, this kind of single Braga, MA Dara, MB single Braga, MB, MC single Braga, MC, and D single Braga, MD, and ME single Braga, ME Dara, and so on. But this quantum circuit can be rewritten by using this quantum circuit. So this part becomes something like this. Again, these parts are also rewritten by using this kind of quantum circuit. And importantly, the quantum circuit depicted in blue are always cancelled out because this part corresponds to this part, and this applying this part and then apply this part. This in this part. So it means applying control Z gauge, single gauge, single gauge, and single gauge, single gauge, control Z gauge. And applying the single gauge twice to the same qubit becomes identity operator. And again, applying the control Z gauge to the twice to the same gauge, same qubit become also identity operator. So the quantum gauge depicted in blue are always cancelled out. So we can reduce this kind of single gauge from the quantum circuit. And this kind of quantum gauge reduction is very powerful, becomes very powerful when the number of qubits increases. When the number of qubits increases, there are many operators having with the large number of qubits between P and Q and R and S. So, but we can reduce the signal rather between P and Q and R and S acting on the qubit inside of the P and Q and inside of between R and S can be cancelled out. Another quantum gate reduction. Let's think about the another quantum gate reduction. And this is the quantum gate set available in IBM Q. We are focused on this operator. This RX gate implements a points of minus I theta over 2 x times x. So this kind of operator appears in the sometimes appears in the quantum chemical calculation. Where I think about the quantum circuit shown here. In this case, where I think about the exponential IG x0 x1 t terms IG, for instance, I minus IG y1 by y1 t terms. So this, the concept corresponding to this time evolution operator can be constructed as shown here. In this case, we apply Agama gauge to transform the basis from X basis to Z basis, and then apply single gauge, and then apply a rotational gauge, and then apply another single gauge and apply another Agama gauge to make the transform to the original quantum state. But this operator can also be written by using a single 2-qubit gauge Rx. And also, this kind of operator can also be rewrite by using if the RYY gauge is available, this becomes just a single RYY gauge. If the RYY gauge is not applicable, but RXX gauge is available, we can perform the same quantum gauge by using S garage and S gauge. The quantum gauge corresponds to S operator is defined as shown here. So it means that this X gauge interchanges from the X basis and Y basis. So in this case, we apply X Gara operator to generate to make the quantum state from X basis to Y basis to X basis, and then perform RYY operators, and then perform another X operator, apply another X operators to change the basis from X basis to Y basis. So this kind of quantum circuit can be also rewrite by using this kind of RYY or RXX gauge. But importantly, if we perform this kind of quantum gauge on real quantum devices, well, think about using the perform the RXX gauge on IBM Q machine. This is the result. In this case, I wrote just a very tiny quantum circuit corresponding to just applying the RXX gauge and measure the quantum state. But transpired quantum circuit is shown here. So in this case, this RZ loop X RZ corresponding to the Agama gauge, and single RZ Agama gauge, and single RZ single RZ single, and apply another Agama gauge. So in this case, the original quantum circuit is written by using just a single RXX gauge, but transpired quantum circuit is just this quantum circuit. So this kind of quantum gauge regression is meaningful if the RXX gauge is available as a base gauge, because the IBM Q machine, the RXX gauge is not applicable directly. So in IBM Q machine, this RXX gauge is transferred to 9 RZ gauge, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 4 root X gauge, and 2 single gauge. So, but and this risk is available in the Amazon bracket service, which can be which is used to access the related machine, IBM IonQ machines. As you can see, IonQ devices support XX and YY and ZZ gauge, this XX and YY CCJ correspond to RXX, RYY, and RCCJ. So it means if we use the ion Q machine, we can directly implement this RXXJ without transpiling the quantum circuit like this. So this kind of quantum gate regression scheme is very machine dependent, but if this kind of gates are available in the real machines, we can reduce the number of quantum gates. And also, another approach for, in some cases, the quantum gate regression can be applicable. It can be done by using the applying different Feynman-Qubit mapping techniques. So let's think about the time evolution operator under the X-square operator. So usually we use the Hamiltonian as a time evolution operator, but here I would like to discuss the time evolution operator under the X-square operator. So X-square operator has an eigenvalue x times x plus 1. So applying this time evolution operator will cause some phase cycle depending on the spin quantum number s, as shown here. So usually this x, in order to perform this kind of operations, we have to just define the x-square operator in the second quantized formula, and then perform the Feynman-Qubit transformation using Jordan-Wegener or Bright-Staff or something to obtain the power operators, and then contrast the quantum circuit. So this x-square operator can be defined in the second quantum formula, as shown here. So x-square operator can be rewritten as a xc term and x plus x minus and x minus x plus terms. And as you can see, these x plus x minus terms is defined as a two electron excitation operators. So if we perform this kind of operation using Jordan-Wegener or Bright-Staff or something, we need a very deep quantum circuit to realize the time evolution operator corresponding to this kind of operators. But x-square operator can also be defined by using the number operator or electron spin NP, and also the permutation operator PPQ. This PPQ interchanges the spin of P's and Q's molecular objects. So you can easily prove that this number operator are commutes, and number operators and permutation operator also commute. But the permutation operators doesn't commute. But anyway, if we use this kind of definition, the time operation operator can be written as shown here using the Trotter decomposition. And the insight of exponential is number operator of electron spins, and this in this case, in this term, it includes permutation operators of spins. And in order to perform this kind of operation, we can introduce another wave function mapping technique named as the general spin coordinate mapping. And in the general spin coordinate mapping, this is a occupation number basis. So it means that Jordan-Wegener cases. In the general spin coordinate mapping, the first qubit stores if the corresponding molecular orbital is open shell or not. And the second qubit represents the occupation number of spin-bit electrons. So that this kind of time evolution operator, this NP corresponds to the number operator of electron spin. So this operator, this kind of an operator can be realized by using a single phase gate. And in this term, this is a product of the number operator or electron spins. Again, this term can be realized by using a control phase gate. And this permutation interchanges from alpha to beta. So in the Joan Wigan case, it interchanges so 1 to 1 0. And but in the general spin cognitive mapping, it interchanges 1 1 and 1 0. So basically, this permutation of this kind of operators can be realized by using a control 1 electron excitation operators. So in this case, we need the 2 control qubits, but basically the quantum circuit corresponding to 2 electron excitation operator is about 4 times longer than the quantum circuit corresponding to 1 electron excitation operators. So by applying this kind of transformation, we can reduce the depth of the quantum circuit. And also, in the case of time evolution operator, we can reduce by using the QDrift method, the quantum gate by using QDrift method. Let us think about the time evolution operator under the Hamiltonian. Hamiltonian is written as a linear combination of pi operators, sorry, pi strings, and WJ correspond to the question. First, we divide the time evolution time t into R segments. So here. So the original time evolution operator can be written as a UR to the R's power. Okay. So usually we have to apply Trotter convolution to this term, but in the QDrift method, we approximate this UR by using this operator. Here, this PJ selects randomly with a probability proportional to the question WJ in absolute value. So let us think about the, as an example, let us think about the Hamiltonian as shown here. It has 5 terms, power C and power C0 and C1 and C0 C1 and S0 S1 and Y0 Y1. In this case, we randomly apply one of the 5 operators with a probability proportional to the question. If so, in this case, we apply -2 times C0 over L with a probability 0.25. And also apply 2 times C1 divided by L operator with a probability 0.20. And you can equally understand that if the this random selection repeats L times, so if the L becomes infinitely large, this approximation recovers original Hamiltonian. Importantly, if the L is very small, in that case, this is just an approximation. So if the L is very small, there are some errors arising from this approximation become large, but this approach is very effective if the number of Hamiltonian power string in the in the Hamiltonian is very large. So when I think about, because the Hamiltonian term scales, the number of Hamiltonian terms scales about the n to the fourth power, where n is the number of qubits. Because Hamiltonian include one electron and two electron operators. So let us think about the, for example, 100 qubit system. In this case, the number of Hamiltonian terms become very large, but we can apply this kind of approach with L is very small number. Let's say if the Hamiltonian term includes the million of terms, but we can approximate the time evolution operator of the Hamiltonian by using L equal, let's say, 10,000 or something. In that case, the number of operators, become about the 100 times smaller than original Hamiltonian, than evolution operator using the original Hamiltonian. So this kind of approach is very useful when the number of Hamiltonian terms increases. So it means the number of qubits increases. For small number of qubits, this approach is, less effective because we have to use sufficient large L in order to make the approximation good. So this technique for final game regression. Finally, I would like to discuss Trotter decomposition error regression. And Trotter decomposition is usually used in the time evolution operators in quantum explanation-based approach, and also in the VQE. If we use the unitary couple answers, the factor operator, this kind of excitation operator, in order to construct a quantum circuit corresponding to this kind of factor operator, we have to apply Trotter decomposition, as shown here, to generate a quantum circuit. Of course, Trotter decomposition is a kind of approximation, so there's equal errors. And importantly, in the case of, let us think about the unitary couple answer in the VQE, Trotter unitary couple answer is not equivalent to the original and Trotter's one. This was proved. This is, we can naturally expect it, but this is discussed in detail in this paper. In this paper, they apply Trotter decomposition to perform the UCCSD calculation with different ordering of the terms and estimate how the energy changes by the ordering of the terms. The result is something like this. So in this case, this is a 6 hydrogen molecule cases. This is the potential curve, and you can see that the dependence of the Trotter term organ in Trotter decomposition become larger for longer internuclear distances. So how to reduce this kind of Trotter error? One approach is discussed in this paper, where I think about the time evolution operator shown here. They investigate two types of the ordering. One is a vertical graphical ordering, or just a dictionary ordering. So in this case, in this organ, the operators apply from I first and X, Y, Z. So first we apply I terms, and then apply X term, and then apply Y and Z, and XI, IIXX, IIXY, IIXC, IIYY, IIYX, IIYY, IIYZ, IICI, IICX, IICY, IICC, IXII, and so on. This is a very simple organ. Another organ is magnitude organ. In the magnitude organ, the time evolution operator is applied. The term is applied in descending order of the question. And they perform the time evolution functionality with randomly changing the so by applying this kind of organ, they found that the magnitude organ is smaller total decomposition error than with graphical organ. So it means that it's better to apply a term with larger question first and smaller question later. And also, there are another techniques. I mean, we usually use first order total decomposition in the, but of course, this is the first order, so it means that there are higher order total decomposition. And in the second order total decomposition, this operator is transformed like this. In the first order total decomposition, we divide it m times and then apply this operator m times. But in the second order, in the first order, this is the numerator is m. But in the second order function, the numerator is 2m. And the first, we apply an operator in the ascending order. And after that, apply a same operator in the descending order. So roughly speaking, the number found there in the second order total decomposition is about twice of the gap in the first order total decomposition. And in my experience, using second order total decomposition with 2m gives smaller total error than the first order total decomposition with m. So second order total decomposition with 2m. Sorry, this is not untrue. I mean, using second order total decomposition with m gives smaller total error than the first order total decomposition with 2m. So in this case, the number of quantum gates is almost the same between the first order and second order decomposition. But in my experience, using the second order total decomposition, it gives smaller error. And also, there another approach to error reduction. Again, this is discuss the organ of the terms in total decomposition. So I already discussed two types of organ. I mean the vertical graphical organ and magnitude organ. In this paper, they discussed the pre-group strategy. So this approach consists of two procedures. First, we divide the Hamiltonian terms into mutually commuting subsets. So we classify the Hamiltonian term so that to generate a subset, so that every operator in the subcase are mutually commute. And then the set cycles through picking the highest magnitude term from each appending this to the order Hamiltonian. So if the Hamiltonian, we can generate the subset A, B, C or something. Let's think about the original Hamiltonian can be divided to subset A, B, C. And Hamiltonian terms in group A are all mutually commute, and also for B and for C. So in this case, first we select the highest magnitude term in the group A and append the operator. And then for next, we select the highest, the term having the highest question in group B, and then select the highest operator in group C. And this question is iterated. So A, B, C, A, B, C, A, B, C, and so on. And inside, so the question is basically the inside the group subgroup. I mean, let's say the group A is in the magnitude order. So in this approach, by applying this approach, the error becomes more smaller than the magnitude order. And also, this is not error reduction, but error mitigation technique. But I would like to introduce some algorithmic error mitigation technique. And this is also applicable for quantum ignition technique. Let us think about the first order Trotter error decomposition. The time evolution operator can be rewrite as shown here by using a first order Trotter decomposition, and the error scale as shown here, or the t squared divided by n. Usually the n, this n, increasing this n is very difficult because the depth of the quantum study depends on the n. But we can decrease this n. Of course, if we decrease the n, the error becomes larger. But let us think about the quantum phase expansion with t over n equal to. If we apply a quantum phase expansion with t over n equal to, we obtain this energy. And true fluxual energy is somewhere around here. So in this case, the increasing n, so going left is very difficult because the quantum study becomes deeper. But we can decrease n, so going right is very easy because the quantum study becomes shallower. So let us think about the situation by applying 2n, the n becomes half, so t over n becomes twice. So t, originally we obtain this energy. And if we apply quantum phase expansion with t over n equal 4, let's think about it, we can obtain this energy. So because the error is linearly dependent, roughly speaking, linearly dependent on the 1 over n, so we can approximate, we can extrapolate the energy result of the error by using this extrapolation. So in this case, we can obtain the mitigated energy of the quantum phase expansion. somewhere here. So in this case, the energy, original energy, if it's somewhere here, and the mitigated energy here. So the error can be decreased by this error mitigation technique. So let me summarize today's talk. So we discussed three types of error and record regression technique. And for the qubit regression, we can reduce two qubits by using the conservation of the spin alpha and spin beta electron samples. And also, we can use the point group symmetry. We can reduce another qubit. And final gate regression can be achieved by using the equivalent of the signal value, or if the RSS and R-value and RCC gate are available, we can use this quantum gate instead of the quantum circuit constructed by using a traditional approach. And also, we can adopt operator specific final qubit mapping technique to reduce the number of quantum gate to realize the time evolution operators. And also, we can use approximate time evolution quantum circuit using QDrift approach. And for the Trotter error regression, we can use the magnitude organ is better to reduce the Trotter error compared with the conventional vector-graphical approach or dictionary organ. And also, the pre-group strategy is more efficient, but the pre-group approach strategy needs Hamiltonian tunnel classification to the subgroup. Also, we can apply algorithmic error mitigation technique to estimate the energy or expression value without Trotter error by using extrapolation. So, finally, I would like to thank Professor Bangladesh and Professor Mukherjee and Dr. Prasanna for organizing this lecture series and people in the center of the quantum engineering research and engineering. This is the centers of research and education in science and technology for organize this lecture series. And I would like to announce that all the lecture slides and additional contents are available at this GitHub page shown here. And also, all the lecture videos are available in the YouTube channel of the TCG CREST. And finally, I would like to thank all the participants to participate in this lecture series. Thank you very much.
Thank you very much, Professor Sugisaki, for the wonderful lecture series. Are there any questions? If not, then I'll once again thank Professor Sugisaki very much for this wonderful lecture series. And I'll request Professor Das to give the vote of thanks. Thank you.
Thank you.
Okay, well, it's my pleasant duty to give the vote of thanks. First of all, I would like to thank and express my deepest gratitude to Dr. Sugisaki for giving a set of comprehensive lectures on, on quantum chemistry, on quantum computers. I'd also like to thank Dr. Prasanna for his for overseeing the organization of this lecture series and for making sure that that these lectures were held, on time and held properly. And I'd like to thank Nishant Diplajyoti and Oinanshu, Anuvrata, and members of the IT team at HPL for the help in organizing these lectures. And my thanks to Professor Devashish Mukherjee for coming up with this idea. The idea of having this lecture series was Professor Mukherjee's, and he also presided the opening lecture by Dr. Sugisaki. Now, about the lectures, I think the lectures were unique. I mean, for that, I'm deeply, deeply thankful to Dr. Sugisaki. I mean, he's definitely, he worked very hard to give these lectures, to organize them, and to present them in a way that's both, very deep and also very interesting. I mean, so he began with the basic concepts of quantum computing and gradually developed the topic and applied them to very interesting cases in quantum chemistry. I think this is what makes it unique. And so as you could tell from the participation, that many people were interested in not only the quantum chemistry aspects, but also other aspects, especially those who are working on topics related to quantum phase estimation and their applications in differential equations. I know Nishant in particular benefited from his discussions with Dr. Sugisaki. And I think it's really an excellent idea to have these lectures available on YouTube. And I mean, for sure, I'm going to listen to them many times. I think I have to listen to all of these lectures carefully and understand them and try to apply them, to my research. And so once again, I would like to thank Dr. Sugisaki for the lectures that were unique and they were absolutely outstanding. And to Dr. Prasanna, Nishant, Dibyajyoti, Professor Mukherjee, and members from our center, the Center for Quantum Engineering, Research and Education, for the help and support, and also the IT team at HPL. Thank you very much to all of
you. Thank you very much, Professor Das. So with this, we'll conclude the lecture series. So